Okay, let's dive right in. Today, we're going to get inside the minds of an elite engineering team to really understand a massive challenge. How do you teach an incredibly complex machine to behave? And listen, we're not talking about just any machine. This is a state-of-the-art hybrid electric cement mixer. We're going to explore the super intricate process of calibrating its brain.
Now this quote here, it really reframes the whole thing in a fascinating way. See, we're not just talking about tweaking a few numbers on a laptop. This is way bigger. It's like conducting a complex orchestra where you're managing the vehicle's memory, its entire nervous system, and the very tools you use to talk to it. It's all about building this rock-solid foundation of trust in the data before you even think about making a single adjustment.
So let's meet our main character, a cutting-edge hybrid electric cement mixer. I mean, it's a beautiful, powerful machine, but it also presents this unique and unbelievably difficult engineering problem.
So what's the big deal? Why is this thing so hard to get right? Well, because it's not just a truck, not even close. The demands on its control system are unlike pretty much anything else you'll find on the road. It has to be a super tough, heavy-duty truck, a high-precision industrial machine, and an efficient hybrid vehicle, all at the exact same time. And this slide just lays out the conflict perfectly. You've got the load, the concrete itself, which is this wild, unpredictable goo that's constantly sloshing around, changing thickness, and even starting to harden. The machine is absolutely massive with huge inertia, but it still needs to make these delicate, low-speed moves. And think about it, it has to perform perfectly on a highway, then in a tight parking lot, and then on a muddy, uneven construction site, all while juggling the crazy complexity of a high-voltage hybrid powertrain.
So, to tame this beast, you can't just jump in and start turning knobs. It doesn't work that way. First, the engineers have to build a digital foundation. They've got to set up a totally flawless communication channel, a high-speed nervous system that lets them see everything happening inside the machine's electronic brain in real time.
Okay, so the key breakthrough here is the move to something called CAN FD. Honestly, it's like upgrading the vehicle's nervous system from an old-school dial-up modem to fiber optic internet. I mean, look at that, an 8x increase in data speed, and the data packets are way bigger. This means engineers can finally see stuff that happens in milliseconds, like the tiny kick from a clutch engaging without the data stream getting all jammed up. It's the difference between guessing what just happened and knowing exactly what happened and when.
Now, think of the A2L file as the vehicle's universal translator and its rulebook all rolled into one. It is the digital contract. It's what tells the tools, hey, this specific memory address controls this specific function. Without a perfect, double-checked A2L file, any tuning you do is just a dangerous shot in the dark. You could think you're adjusting the gas pedal, but you might actually be messing with a critical torque limit.
And this right here, this just shows you the incredible discipline involved. The team lives and breathes by this rule. That digital foundation, that contract, has to be absolutely perfect and peer-reviewed before anyone touches a single setting on a real vehicle. It's all about building that trust. There are no shortcuts.
All right, so now we can talk to the beast, but how do we teach it to do something very specific and very high stakes? Let's zoom in on controlling that giant mixing drum. It has to spin at a constant, precise speed, whether it's totally empty or full of 40,000 pounds of concrete.
To get the drum under control, engineers use this methodical process called PID tuning. It's been the bedrock of control theory forever. And here's the wild part. They start by intentionally making the system a little unstable. They crank up the proportional gain, that's the P, until the drum's speed starts to oscillate, to wobble a bit. This tells them exactly where the edge of stability is. Then they back it off a little and carefully add the integral gain, the I, to nail the target speed perfectly. And finally, the derivative gain, the D, to smooth out the response and stop it from overshooting. It really is a delicate balancing act.
And here you can see the art behind the science. This is a simple little memory trick that the senior engineers use to teach the new folks. P is for power, how fast the system reacts. I is for integrating out any error to make it accurate. And D is for damping, which makes the drum spin look smooth and effortless. You see, it's not just about making it work, it's about making it look graceful. But here's where it gets really clever. A single set of tuning numbers just won't cut it for both an empty drum and a fully loaded one. It's just too different. So, the engineers use something called gain scheduling. Based on how much concrete it thinks is in the drum, the control unit automatically switches to a whole different pre-tuned set of PI and D values. This ensures you get perfect, stable control no matter what.
Okay, let's move from the giant mixer in the back to the driver's seat up front. The feel of a vehicle. Is it smooth? Is it jerky? That's all super subjective. So how on earth do engineers turn a feeling like jerkiness into a math problem they can actually solve?
This is a fundamental truth in vehicle tuning. That harsh kick or lurch you sometimes feel when you accelerate, it's almost never about the engine having too much power. It's about that power being delivered too fast or at exactly the wrong split second. The problem isn't the what, the amount of torque, it's the when.
So the key is to tackle something called the torque hole. In a hybrid, when the gas engine is kicking in, there's this tiny moment, a gap, where the power delivery dips. To the driver, it feels like a hesitation. The solution is torque fill. This is where the electric motor, with its instant power, acts like the perfect dance partner. It flawlessly fills that little torque gap while the engine gets up to speed, making the whole transition totally invisible to the person behind the wheel. And this proverb really sums up the whole philosophy. This isn't about brute force, just throwing a ton of electric torque at the problem. No, it's a precisely timed ballet between the engine and the motor. The goal here is surgical precision, not overwhelming power. So, after all this delicate, painstaking tuning, how do you lock it all in and guarantee it's safe enough for the real world? This is where the process gets incredibly strict, governed by global safety standards like ISO 26262.
Every single collection of calibration data has to go through this strict maturity model. It starts as a draft version that's only allowed in the lab, and it works its way all the way up to a release candidate. Nothing gets close to the production line until it has passed every single one of these stage gates, survived testing in every imaginable condition, and has finally locked in as the golden master.
So the huge takeaway here is that safety is not an afterthought. It's baked into the DNA of this entire process. Critical settings are literally locked as read-only, so they can't be changed by accident. The vehicle's computer checks its own instructions every single time it starts up using a checksum. If even one bit of data is off, it goes into a safe mode. And every single promotion from one level to the next is documented, reviewed, and justified. Absolutely nothing is left to chance. And this, right here, is the ultimate goal. It's not just about building a machine that works smoothly on a perfect day in a lab. It's about engineering a machine that is predictable, that is reliable, that is trustworthy, no matter what the world throws at it. A machine that guarantees no surprises. What an incredible engineering challenge. And frankly, an even more incredible achievement.